Hello! In our final Chapter 6 video, Lecture 16, Learning Objective 11, we're going to be looking at condensed electron configurations, we're going to be looking at anomalous electron configurations, and we're going to be looking at magnetism. Okay, so we're going to bring into the idea, or into our bank of knowledge, the idea of core electrons and valence electrons. So a core electron is going to be one that is an inner shell electron. And then a valence electron is called a outer shell electron. Okay, so if we're looking at something like carbon, if we did the electron configuration for carbon, we'd have 1s2, 2s2, 2p2. So our core electrons in this case are our inner shell electrons, so they're the ones with the smaller values of n than the max value. We see that our max n value in the case of carbon is n equals 2. So our core electrons are going to be n equals 1. So they're going to be our 2 1s electrons. So core electrons here, or these right here. Our valence electrons are those with the max n value. And our max n value here is 2, so they're going to be our n equals 2 electrons. So they're going to be our 4 electrons, or 4 electrons in 2s and 2p. So our valence electrons are going to be these electrons right here. Okay? So this is really easy for any main group element. So anything that's in our S block, anything that's in our P block. It's really easy to determine what our core and valence electrons are. Try again. We have argon. Argon has electron configuration 1s2, 2s2, 2p6, 3s2, p6. Our max n value is n equals 3. So our valence electrons are these 8 electrons right here. Our core electrons are these 10 right here. Very simple. Until you get to something that is in the middle of the periodic table. And what I'm talking about here, of course, are transition metals, because our transition metals can't behave like anything else. Let's take iron, for instance. Iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So I said that the max n value gives us our outer shell electrons, but that is not true if we're talking about a transition metal. With a transition metal, because our S and our 4s and our 3d overlap, we're going to actually have to take these as our valence electrons. So these are the valence electrons in this particular case. And then our core are these. If you write it out according to the Aufbau principle, you're basically going to see, okay, where do I have my highest n value? Wherever that starts, you can go ahead and cut it off. Okay, for transition metals. Now, again, if we have something that's a little different, such as, let's see, let's take gallium. Gallium is again a little weird. Or it's, I guess, back to normal would what we'd say. Okay, going to gallium, we're going to go back to our normal description where our max n value are our valence. Anything less than the max is core. So these are all core. And so are these. So the only case where we have a less than n max in our valence is a transition metal. So here, this one goes with these. Okay, so again, very weird for our transition metals. Anything besides transition metals, our core electrons are n minus 1 or less. Our valence electrons are our max n value. With our transition metals, we're going to include the d orbitals, the n minus 1 d orbitals into, or d subshells electrons into that valence because we are actively filling that shell, subshell. Okay, so next thing I want to look at is the idea of a condensed electron configuration, or a noble gas notation, or a shorthand version. They're all the same thing. So a condensed electron configuration is a shorthand notation. So instead of writing all of this out, we have a shorthand notation to make it a little bit simpler. So what we do, we also got, or noble gas notation, is we use our noble gases. So let's look at gallium again. And we're going to look at gallium, and then we're going to go the row above it and look at what noble gas is at that row. So we're going to look at the row all the way to the right. And if we look for gallium, the noble gas before it is argon. Okay, so we already talked about argon. Argon has this electron configuration, so I'm going to write it back out. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. Gallium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. And then if we look, we see that this is the same in both. So we're going to use our noble gas to basically account for these electrons instead of having to write them over again. So we're going to write AR for all of those electrons, and then 4s2 3d10 4p1. So this is our condensed or shorthand notation or noble gas notation for gallium. So the argon is just in there to account for those electrons of argon. So instead of writing them over and over again. Okay, so let's look at some anomalous electron configurations. So electron configurations that are a little bit weird. So some electron configurations appear to violate the rules. So they don't follow all of the same rules that we're used to seeing or that we've seen so far. And the reason they do this is because they're trying to get to a more stable state. So our irregularities will occur when there are enough electrons to half fill or completely fill a D or F subshell. Keep in mind that our D and F subshells have got so many electrons in them that they repel, but this half-filled or full-filled state is an energetically favorable state because our spins are paired up. We have a spin up, spin down. So that's going to decrease the energy of those states and bring that energy down. So if we think about something like chromium, we would expect chromium to be AR, so taking that argon, AR, we expect it to be 4s2 3d4. But what happens is we are so close to a half-filled state, one of these electrons will promote to there to give us a half-filled state 4s1 3d5. So this is half-filled, which is energetically favorable. Okay, we see the same thing in copper. So copper, you would expect it to go AR, 4s2, 3d9, but instead we're going to promote one of these. So that we can get that full filled state. Again, energetically favorable. And then if we look down in our F block elements, we can look at gadolinium. Gadolinium, we would expect it to be Xe, 6s2, 4f8, 5d, or sorry, just that. But instead, what we get is Xe, 6s2, 4f7, 5d1, because now, again, we have the ability to do a half-filled state. So those are our anomalous ones. We will also look at electron configurations for ions real quick. So our ions are going to be easy if we're talking about main block elements. So main block elements are going to add and subtract electrons in order to get to a noble gas electron configuration. So these are pretty easy to do. There's usually no anomalies here. So if we take, for instance, N3 minus versus nitrogen, nitrogen would be 1s2, 2, oops, 2s2, 2p3. Our N3 minus, we're going to add 3 electrons into the p orbital. So let's arrange that a little bit better. N3 minus, we add 3 electrons, and that will go into here because we have a maximum of 6 electrons we can fill. So this would be 1s2, 2s2, 2p6. So very easy. And all main groups are going to be like this. Let's take magnesium versus magnesium 2 plus. Magnesium is 1s2, 2s2, 2p6, 3s2. Losing those 2 electrons, we're going to lose these 2 electrons and we'll go to 1s2, 2s2, 2p6. So our main group elements are going to have ions that have a noble gas configuration, electron configuration. Our D block, or I guess ions, we're going to remove the highest N value electrons first. So in this case, let's look at iron again. Let's look at iron 3 plus. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. We need to remove 3 electrons, so we'll lose the highest N value electrons first, so those right there, and then 1 from there, giving us 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. F block. We're going to remove s electrons first, then d electrons, then f electrons. So let's take our gadolinium, for instance. So gadolinium is Xe, 6s2, 4f7, 5d1, and gadolinium 3 plus. We're going to remove these electrons and this electron, So we'll just have 4F7. Pretty easy. Last thing I want to talk about is magnetism in atoms or ions. So when we have an electron that has a spin, that's going to allow it to be magnetic, right? So if we have in the orbital diagram, we see that we have unpaired. Then we're going to have an unbalance between the spin up and spin down. So if we have an orbital that just has one electron in it, and we don't have another electron paired up with it, we have an unpaired electron. That unpaired electron has a greater amount of spin up than spin down, so this will be called paramagnetic, and it will actually align with a magnetic field. If all electrons in the orbital diagram are paired, this won't be magnetic. So here we have all of them paired like this, and we call this diamagnetic. So this one will not align, or it will actually be repelled by a magnetic field. This will align with that magnetic field. Paramagnetic magnets are the ones that you see in stuff like your card readers, which is why if you introduce a card reader or a credit card to a magnet, it can erase that magnetic field in there. We are done with chapter 16. Goodbye, everybody.